Welcome to Calculus. Today we are diving into one of the most elegant and powerful tools in all of mathematics, Lagrange multipliers. If you have ever wondered how to find the absolute best outcome when you are forced to play by strict rules, you are in the exact right place. Let us get started on this journey. To understand what we are doing, imagine you are hiking a massive mountain. Your goal is to reach the highest elevation possible. But there is a strict rule. You must stay on a specific marked trail. The mountain's elevation is our objective function, the thing we want to maximize. The trail is our constraint, the rule we must obey. We want the highest point on that specific trail, not necessarily the mountain peak. This method finds that point elegantly. Now that we have our hiking analogy, let us look at this mathematically. Here, the concentric ovals are contour lines representing different heights on our mountain. The solid black curve is our trail, the constraint. Notice the point labeled P. This is the highest point on the trail. At this exact spot, the trail just barely touches the contour line, running perfectly parallel to it. Because they touch perfectly, their steepest uphill directions, called gradients, point along the exact same invisible line. This visual alignment of gradients gives us our foundational equation. The symbol nabla represents the gradient, pointing in the steepest uphill direction. F is our objective function and G is our constraint. Because the gradients are parallel at the maximum, one is just a scaled version of the other. That scaling factor is lambda, our Lagrange multiplier. If you move away from this point, the gradients no longer align, meaning you either break the rule or drop to a lower height. To make solving this easier, mathematicians combine the goal and the rule into one master equation called the Lagrangian function, denoted by a cursive L. We take our objective function and subtract lambda times our constraint equation, set to 0. By taking the partial derivatives of this new master function with respect to every variable and setting them to 0, we simultaneously find our maximum and ensure our rule is perfectly followed. As the constant c increases, the constraint loosens. Before we calculate anything, let us understand what lambda actually means physically. It is not just a random algebraic stepping stone. The value of lambda at the optimal point tells us exactly how sensitive our maximum value is to a tiny change in our constraint. In economics, this is called a shadow price. If lambda is 5, relaxing your constraint by 1 unit increases your maximum profit by $5. If lambda is 0, the rule is not actually holding you back. So, we have found a critical point using our Lagrangian, but we have a problem. That point could be a maximum, a minimum, or even a saddle point. To confirm exactly what kind of point we have found, we must use a second-order condition known as the bordered Hessian test. Relying purely on physical intuition can sometimes lead to incorrect conclusions in complex spaces. So this mathematical check is absolutely crucial to ensure we have the right answer. This brings us to the bordered Hessian determinant formula. It is a grid made of the second partial derivatives of our Lagrangian, bordered by the first partial derivatives of our constraint. By evaluating this determinant at our critical point, we get a single summary number. If this number is strictly greater than 0, we have confirmed a local maximum. If it is strictly less than 0, we have a local minimum. This organizes how slopes change in every direction. Up to now, we have assumed our rules must be met exactly, like a perimeter of exactly 40 meters. But in real life, constraints are often inequalities, like a budget you do not have to fully spend. To handle this, we use the Karush-Kuhn-Tucker or KKT extension. It introduces a logical check. If the true peak is inside your budget, lambda becomes 0. If it is outside, you push until you hit the limit and solve it just like a standard equality constraint. Let us see this in action with a classic problem. A farmer has exactly 40 meters of fencing and wants to enclose a rectangular garden to get the absolute maximum area. Our objective function is area, x times y. Our constraint is the perimeter, 2x plus 2y equals 40. We build our Lagrangian by taking the area and subtracting lambda times the rearranged perimeter constraint. This sets up our master equation. With our Lagrangian built, we find the critical points by taking partial derivatives. First, the derivative with respect to x gives us y minus 2 lambda equals 0. Next, the derivative with respect to y gives us x minus 2 lambda equals 0. Finally, the derivative with respect to lambda simply returns our original perimeter constraint set to 0. We now have a system of 3 simple equations to solve for our variables. From our first 2 equations, we see that both x and y must equal 2 lambda. This means x equals y, so the optimal rectangle is actually a square. Substituting this into our perimeter equation gives 4x equals 40, meaning x is 10. Our mathematical solution tells us the width is 10 meters, the length is 10 meters, and lambda is 5. The maximum area is 100 square meters, and an extra meter of fence adds 5 square meters. Before we celebrate our maximum area, we must rigorously verify it using the bordered Hessian test. This chunk of our proof establishes that our critical point is a true peak rather than a valley or a saddle point. We need the first derivatives of our constraint, which are simply 2 for x and 2 for y. We also need the second derivatives of our Lagrangian function. The second derivative with respect to x twice is 0, and with respect to y twice is also 0. The mixed partial derivative is exactly 1. This perfectly sets up the matrix we need for the final calculation in the next step. Now we plug these calculated derivatives into our determinant formula. Calculating the determinant of this 3 by 3 matrix evaluates to positive 8. Because the number 8 is strictly greater than 0, the second order condition confirms mathematically that our critical point is indeed a local maximum. The intuition here is that the curvature of our combined function, when restricted to the trail, guarantees we are standing at the very top of the hill. We can also verify this entire solution using basic substitution from single variable calculus, which yields the exact same result. This independent check proves our method works flawlessly. What happens when we have more than one rule to follow? For example, minimizing the weight of a bridge while ensuring it is strong enough and tall enough. The method of Lagrange multipliers scales up perfectly. Instead of just one constraint gradient, we now have multiple. We simply assign a unique Lagrange multiplier to every single constraint and add them all together to form our new equation. In this expanded formula, the steepest uphill direction of our goal is now a blended combination of the steepest directions of our rules. We have lambda 1 for the first rule and lambda 2 for the second rule. When building the Lagrangian function, we simply subtract lambda 1 times the first constraint and then subtract lambda 2 times the second constraint, taking derivatives just like before. The math remains beautifully consistent. Let us look at a complex example involving 2 rules. We want to find the point in 3-dimensional space closest to the origin that lies on the intersection of 2 flat planes. Our objective is the distance squared. Our 2 constraints are the equations of the planes. We build our master equation with 5 variables, x, y, z, and our 2 multipliers, lambda 1 and lambda 2. This sets up our optimization. Taking the partial derivatives with respect to x, y, and z gives us 3 equations, plus our 2 original constraint equations. By solving this system of 5 linear equations, we find the exact coordinates. The point is 4/3, 1/3, 4/3. This specific point perfectly satisfies both plane equations and has the absolute minimum distance to the origin. The multipliers would tell us the sensitivity to shifting the planes. Now that we have solved these complex problems, it is easy to see why this method is one of the most powerful tools in applied mathematics. In economics, it models consumer behavior. In engineering, it optimizes airplane wings. In physics, it forms the foundation of classical mechanics. Without this method, solving these constrained problems would require impossible algebraic substitutions, making modern optimization software completely unworkable. Let us summarize what we have learned. Lagrange multipliers allow us to find the maximum or minimum of a function while strictly obeying rules. By setting the gradients parallel, we find where our goal aligns with our limitations. The multiplier reveals the shadow price, and the bordered Hessian ensures we found the correct extreme point. You now have a powerful new tool in your calculus toolkit. Great job today.